Alright, welcome to 1.08. We're going to take a look a little more closely at piecewise functions and consider where they're continuous, where they're discontinuous. Make sure we have a really good handle on a strategy for when we want to evaluate the continuity of a piecewise function. And then we're going to take that and extend it in order to make piecewise functions continuous. So identify a discontinuity and then somehow manipulate the function or extend the function to make it continuous. Alright, let's start with a piecewise function, a little refresher for those of us who are feeling not so great about it. A piecewise defined function is a function that combines multiple functions over its domain. So as we've seen in the past, right, you have some piecewise function, and the reason it's called piecewise is that it's broken up into pieces. So, you know, for the x values that it's defined, maybe it breaks it up into two pieces. So it says, look, if you go, for all x values less than 0, use this function. But then for all values greater than or equal to 0, use this function. And so it's just a way of breaking up your domain into different functions. So let's take a look at an example here and use this kind of as a motivating example for us to identify points of discontinuity and where the function is continuous. So if I have this function f of x is equal to x plus 3 when x is less than 0, and it's equal to x minus 3 when x is greater than or equal to 0. So one thing that I like to do when I am graphing a piecewise function, if that's something I need to do, is to just split up my x-axis, okay, and really identify where the split happens. So here there are two pieces. One which is for all x values less than 0. So that's going to be everything over here, not including the y-intercept, right? And then the next piece, the right side, so to speak, is going to be when x is greater than or equal to 0. And so that's everything over here, including the y-axis, because it equals 0 as well. So now that I have that split up, I'm ready to graph. And so I just take it one step at a time. And so this function, x plus 3, is for all x values less than 0. Now, what I'd like to do is plot a couple of points, maybe to visualize it, or if I know exactly what it's going to look like, I can just go ahead and sketch through. There is one key point to keep in mind, and that is, look, it's not defined for 0, right? But I want to go all the way up to 0 and make the point that it would be at if x were equal to 0 as an open point. And that's very important because that'll allow us to more clearly see the discontinuity. So I'll plug in a couple of values here. So for example, if I plug in -3, -3 plus 3 is 0. That's the root or x-intercept. And then it might be helpful to go ahead and just plot what it's going to be at when x is equal to 0 as an open circle, right? Because it's not defined at that point. So if x were equal to 0, I'd have 0 plus 3, or 3, and I need to make that an open circle. And so now I can just sketch the first part of my function. Now, the next part of the function is for all values greater than or equal to 0. So this is much more clear in that I want to start at 0 and work my way out. So we should do that. Start at 0. 0 minus 3 is -3. I'll graph it in a different color here. 0 minus 3 is -3. And this is a closed point. Okay? And we should be able to see that this is a linear function with a slope of 1. And so it's just going to go out this way. But if you needed to, you could plot another point, maybe when x is 3. So if you plug in 3, it'd be 3 minus 3, which is 0. And we can make a little guesstimate and plot that point somewhere over here. And so, as I might expect, this is the right side of my function. Alright, so now what we want to do is determine the continuity of the function. And so if we think about each of these kind of as an individual piece, and we just think about the continuity of each piece, that should really be able to synthesize our work. so that all we have left is some points of concern that we can evaluate more closely. So let's first start with the x plus 3 side of the function, and this is just a straight line, right? So it's going to be continuous everywhere. And then I look at the right side of my function, and this is x minus 3, another straight line, and so this is going to be continuous everywhere. So I know that this piecewise function is continuous everywhere, and there might be one point where I'm not so sure, and that is the breaking point, right? X equals 0. And so what I'd like to do now is, now that I have this point of concern, I'm going to evaluate the limits, right? I go back to my definition of continuity. You might want to do that now. And for a function to be continuous, well, we need the limit as x approaches that value, that x value, in this case 0, to be equal to the function at that x value. Okay? So we can evaluate the limit as x approaches 0 of f of x. And what we're wondering is, will that be equal to the function at 0? So let's go ahead and take a look maybe at the right side first. The function at 0 is defined as the y value 3. And what about the limit as x approaches 0? Well, this is a two-sided limit, so we have to evaluate the left side first. That limit is 3, and the right side, that limit is negative 3. So that does not exist, and since it does not exist, it cannot be equal to 3, and so not equal, and therefore not continuous. And then we want to make sure that when we say something is not continuous or discontinuous, we want to make sure we mention the type of discontinuity that it is. So perhaps go back quickly and take a look at the different types of discontinuities, and this way we can then classify it. And this would be classified, so this function, so we could say f of x not continuous at x equals 0. We have a jump discontinuity. Okay? Now, whenever something is discontinuous, what we want to be able to do is think about how we could manipulate, maybe expand, do something to our function definition so that it then becomes continuous. And so if you go back to your definition of continuity at a point, and this is going to be very important, we need the limit as x approaches 0 to be equal to the function at that value 0. And so our question is, what could we do so that this limit, first off, has to be defined and then is equal to the value at 0, or f of 0. And there are actually two options here, right? What I could do is I could move this part of my function, the right part of my function, up 6 units, or translate it vertically 6 units. Well, in that case, to translate this 6 units, I would have to add 6 to it, and that would make it x plus 6. That would make it continuous. Or I could translate this part of my function down 6 units, so x plus 3 minus 6, which would bring it down to x minus 3. So that would make it continuous at x equals 0. Okay, so what I'm going to do is I'm just going to go ahead and write out the three steps that are pretty basic to us being able to identify continuity and discontinuity, points of discontinuity for a piecewise function. Alright, so just to recap, first things first, we're going to evaluate each piece of the piecewise function on its own, and that will help us take a stock of the function overall and identify the possible points of discontinuity. So once we've identified those, step 2 is going to be to evaluate those possible points of discontinuity. using the definition. Always when we're evaluating something like discontinuity, we go to the definition of continuity and make sure that we test the definition, right? Does it fulfill all of the criteria in the definition? So we're going to use limits here. Then I've identified a point of discontinuity. If we want to make it continuous, what we need is each piece must have the same one-sided limit. So as we saw here, each of these pieces must have the same one-sided limit in order for them to be continuous. Alright, so let's go ahead and try these out. Go ahead and copy them down and give them a try on your own. Make sure for part B that you justify. So go back to the types of discontinuities that we discussed and make sure that you know for each one what has to be the case as far as the limits, one-sided limits go. And use that to justify. So give this a try and we'll discuss very briefly, but you can compare your answers with your classmates tomorrow. Alright, so for number 1, here you can construct a graph if you'd like, if that helps you visualize, but if not, you don't need to, because you can decide each piece, whether it's continuous or not, on its own, and it shouldn't be too hard to figure out the points that you're concerned about. But if you do need to graph it, go ahead and construct a graph. For number 2, follow our same criteria for evaluating discontinuity of piecewise functions, and make sure that you classify each discontinuity as a particular type. Okay, here is a free response problem, similar to something that you would find on an AP test. So there's no calculator. This would be a no calculator section question, and has 2 parts. So the first is to find the value of k so that f is continuous at x equals 1. And then part B is using this k value that you found in part A, sketch a graph of fx. So go ahead and copy this down and use your definition of continuity at a point to solve for A, and then go ahead and sketch B. You can do this, so give yourself some time, trust the definition, trust yourself. Okay, don't just assume that you've got the wrong way of doing it because you might not be sure. Okay, give it a try, and I think you'll find out that you're going to do just fine. So for part A, if we want f to be continuous at x equals 1, the first thing that we need is we need the limit at x equals 1 to exist, which means that we need the left-hand limit and the right-hand limit to be equal. Okay, so that's the first part. Now, the second part would be for the function at 1, so f of 1, to be equal to this limit. Okay, so let's consider that second part after we make sure that the limit is equal to each other. So think about how you would evaluate the limit of this function. Well, this is a continuous function, right? No matter what the k value is, this is just a straight line with slope k. So to evaluate this limit, you would just plug in the value 1 into this function. So you would have k times 1 plus 1 is equal to, now over here, same idea, x squared is always continuous. So I would just plug in the value 1 to find the limit as x approaches 1. 1 squared. So now, if I continue solving, I have 1 is equal to k plus 1. So that means that k must be equal to 0. Okay, so if k is equal to 0, then what will these limits be? Well, let's think about it. If k were equal to 0, then we'd have is 0x plus 1. Okay, and well, wait, yeah, 0 times x, that's just 0. So this is the constant function 1, right? Y equals 1. It's a nice horizontal line. And so then the question is, will the limit as x approaches 1 from the left of 1 be equal to the limit as x approaches 1 from the right of x squared? Well, let's test that out. Limit as x approaches 1 from the left of 1. Well, constant function 1 is always going to have a limit approaching 1. So that's just equal to 1. And the limit as x approaches 1 from the right of x squared, again, this is a continuous function everywhere, so I just plug in 1 and 1 squared is 1. So sure enough, the limit exists and is equal to 1, and now we just need to make sure that f of 1 is also equal to 1. So this would be criteria 1. Now criteria 2, we need to know what f of 1 is. Well, when x is 1, we're using this part of the function, and so we'd have 1 squared, which is equal to 1. And so we have now the criteria for continuity satisfied with a k value of 0. So now with k value of 0, let's go ahead and just put that in. And to put that in, we'll just get rid of it, this piece here, because 0 times anything is 0. So now we can go ahead and sketch a graph of this function. And if you haven't already, I encourage you to go ahead and try this on your own first. So when x is less than 1, and let's put 1 right here. When x is less than 1, the function is equal to y equals 1, right? That's pretty simple. And it's less than strict, so there's an open circle here. Okay. Now, when x is greater than or equal to 1, we have x squared, which means we include the value at 1, so it's going to be a closed point. 1 squared is 1, and so we are actually filling in now this point at 1. And it's just a squared function, right? So we know what that looks like. Just a simple quadratic. And there's our function. All right. Hope that went well. I'm going to give you one more problem to try on your own, and we can discuss it in class tomorrow. All right, here are a couple problems for you to try. Notice that the first one is from the book, page 85, number 47. And the second one is a great multiple choice question, an AP style type question. So take your time here. Remember, try them on your own, then go back to your notes to confirm that your answer is correct. Right? You should be showing up with an answer you feel really, really confident about so that you can move on and be successful on harder, more challenging questions.